Okay, hi everyone. Let's get started. So, Professor Han is joining a meeting, is attending a conference today, so he is not here. So I will give this lecture on his behalf. So firstly, happy Halloween. So this is also my first time doing this. So if there's any questions, problems, feel free to let me know and just interrupt me. So today we are going to talk about efficient GANs videos and also point cloud recognition. So over the previous lectures, we have talked a lot about domain-specific, like general efficient deep learning techniques, for example, like model compression or pruning or distillation or neural architecture search. So by general, it means that these techniques can be applied to various domains. So at the same time, we also have a lot of application-specific optimization opportunities. So that is what we are going to cover in this lecture. So it will be three parts. The first is GANs for image generation, and also the second is video recognition, and the third is for point cloud processing. So let's first start with efficient GANs. So GAN, or generative adversarial network, is a kind of model that is the state of the art before the diffusion models. Of course, nowadays diffusion models get super popular, so it generally takes over. So this is the general idea of a GAN model. So the main idea is to generate image by adversarial training. So the system consists of two parts. The first part is the generator, and the other part is the discriminator. So the generator generally takes a random noise as input, and then it will generate some samples. And for the discriminator, it will take the samples from both the generators, which is the fixed samples, and also the real samples, for example, some images. And the task of the generator is to generate some realistic samples, or the discriminator's task is to tell if the input image is real or fake. So during the training, the generator and discriminator are trained iteratively. So by iteratively, we mean that for one iteration, we are freezing the discriminator and calculate the loss to guide the training of the generator. And on the next iteration, we are freezing the generator and train the discriminator. So the training objective of the generator, of course, is to train it to generate good enough samples to fool the discriminator to believe that the sample is real, while the discriminator's task is to distinguish between real and fake samples. So these two parts are trained in an adversarial setting so that they are improving at the same time. So this is also bringing some of the problems because we want to maintain the balance between the generator and discriminator. Otherwise, the training will collapse. Like say, for example, the discriminator is too strong, then the generator never has a chance to fool it. Then it will not self-improve. So that's the basic idea of GANs. So for inference, we're actually only using the generator because we use it for image generation, and we no longer need the discriminator because it's only used during the training. Here is a toy demo for the GANs. So this is for training GANs on MNIST dataset. So as you can see, during the random initialization, the generator generates basically all the noise. And during the training, it gradually learns to generate some realistic handwritten digits with the help of the discriminator. So there are a couple different settings for GAN models. One is the conditional GAN, and the other is unconditional GANs. So this is unconditional GANs. By unconditional, it basically means that the generator is only taking a noise, which usually is a Gaussian noise, and it will map the noise into a specific output image. For example, there are multiple of cats. And because it's unconditional, so only the noise is fed to the generator. And on the other hand, there are also some conditional GANs. By conditional, it means that the generator and also the discriminator will take some conditioning apart from the noise. The conditioning can be various of types. So for example, if you're training on ImageNet, it could be just class labels, or it could be some segmentation mask or segmentation map. Or in other cases, it could be stroke. For example, here is a stroke to image synthesize example. Basically, the model is trained provided the strokes for human, and the model is trained to generate image that matches the stroke. So conditional GANs are more popular nowadays because it can be used to do some useful tasks. For example, like image generation from user input or something like that. And here is an example. Oh, sorry. Here is an example of the conditional GANs. So this is the GAN from NVIDIA. It's 3 or 4 years ago, but it was state of the art at that time. But basically, the task here is to map the user drawing. So this is the segmentation map, basically, into some like realistic landscape photos. So it was in the Photoshop for one time, but I don't know if they are still keeping it. And of course, like maybe what's more popular nowadays is a diffusion model. This is the DALL-E model. Like for image editing, you can like actually insert a coggy here in a pretty convincing way. People don't usually notice the editing. So despite the powerful capability of the GAN models, the problem is that the GAN models are usually very computation intensive. So here we show the comparison of the computation and also the model size of different models. So the first two models are MobileNet and ResNet, which are discriminative models. So these are some ConvNets used for feature learning or some like image classifications. While on the lower side are CycleGAN and GAN, which are two quite representative generative models. So as you can see, the computation or the model size is orders of magnitude larger compared to the discriminative models. So this kind of larger computation will make the inference of these models super slow, especially on edge devices. So that is why we need some efficient techniques for these GAN models. So in this section, we'll introduce 3 work from one is GAN compression, how we compress those models with NAS and distillation. And second is anycost scan, how we can train a model that has dynamic inference cost so that we can use it for fast preview. And lastly, we are presenting a data efficient ways to train those GAN models. So let's start with GAN compression. So this is quite similar to the work we introduced before about neural architecture search and also distillation. So the basic idea is that given a pre-trained large generator, we want to distill it into a smaller student generator. So we are doing this by using neural architecture search. So when doing the distillation, there are 3 losses. So it's more complicated compared to like image recognition models where basically you just have one loss function. So the first loss function is the reconstruction loss. So if it is a like conditional generation, for example, we are mapping a horse to zebra, then simply we are asking the model to reconstruct the output. But if this like unpaired training, then we are converting into paired training by distilling from teacher's final outputs. Like here, we are using the teacher's output to train the students. And we find that supervising on the final output is not enough. So we also add distillation loss to the intermediate of the feature maps. So as you can see, because the student model is smaller in terms of channel size, so we need some kind of linear mapping to match the dimension to the teacher model so that we can map it to the same shape and properly calculate the loss. And finally, this is the GAN loss as we talk about. So one part we are trying to train a discriminator to tell the difference between real and fake samples. And on the other side, we are training the generator to fool the discriminator. So the final training objective is the 3 terms combined. There's a lambda term we need to tune. So this is also another limitation of GAN models. Sometimes you do need to do hyperparameter tuning for the loss terms because you need to balance the generator and discriminator. But we're going to omit the details here. And with this kind of distillation loss, we are training a super student generator. By super, it means that this is a super network similar to the one you used in the Lab 3 neural architecture search. So we are training the student generator to run in various channel configurations so that we can, given a fixed budget, we can search a specific student generator at a given cost so that we can have a flexible cost and performance trade-off. So the basic idea is quite simple, just using distillation and NAS for GAN models. But the performance is actually quite good. So here we show 2 models. One is the stroke to image data set on shoes. So this is from original cycle GAN models. I'm sorry, the pix-to-pix model. So this is the ground truth because we actually extract the strokes from the images by edge detection. So the original model produced something like this. And with our method, we are able to compress the model by about 12 times in terms of computation. and the output are still quite is still similar in terms of quality. But because for stroke to image, actually for the same stroke, you can get different outputs. For example, different colors. So the output does not exactly match between the models, but they have the roughly similar visual qualities. And on the right-hand side is the cycle GAN model. So this is horse to zebra application. So this is actually an unpaired training because we don't have a paired data for horse and zebra at the same composition and same pose. So the model is actually unsupervisedly learned to align between the two domains. And with our method, we are able to compress the model by 20 times while maintaining the visual quality. And this is a baseline method. For example, we simply train a smaller model, smaller cycle GAN models with about 15 times smaller computation. But as you can see, the quality degrades a lot. So the model is not able to map those zebra patterns onto the horse anymore. So by compression, it's definitely better compared to training from scratch. And here is also another larger model called GAN. So we are training the model to generate cityscapes or like driving scenarios given the segmentation map. So again, we are obtaining the roughly similar quality given the same input. And here is a demo that we are deploying the compressed cycle GAN for horse to zebra application on an edge device, edge GPU device, Jackson Xavier. So the acceleration is quite significant. Let's look at it again. So on the upper side is the original model, so it runs only 12 FPS, and on the lower side it runs about 40 FPS, so it's quite real time. So this concludes the GAN compression work. So next, let's talk about any-cost GAN work. So another way to use GAN for image editing, for example, you want to add a portrait, is to first train a GAN that generates a portrait given a latent code, W. So given such a GAN model, we can first project the image into the latent space. By projection, it means that we try to find a specific latent code, W star here, so that the model, when given the W star code, can generate a very similar image compared to original inputs. And then we can calculate some like pre-computed editing directions in the latent space, which is the delta W. For example, we can increase the smiling on the person's face and also make its hair to be whiter. So after modifying the latent code, we feed again the latent code into the GAN model and to generate a modified image. So that's another way to use the GAN model for image editing. So the problem again is that the synthesis process is quite slow because the GAN model is so computationally inefficient. So imagine if you want to do this kind of adjustment with all the slide bars, you'll probably want to make multiple adjustments for each of the slide bar to get a desired outputs. So this kind of slow inference will make the interaction quite laggy, so it doesn't provide you an interactive feedback. So we take inspiration from the traditional rendering pipeline. So people, when they try to do a rendering of a 3D scene, they don't always just render to the final result during every adjustment because it would take you about minutes or hours to finish the rendering. So when people do the rendering, they just first generate a low quality rendering, for example, something like this, to help you adjust the layout and also the scene or the lightings. And after you finalize everything, you hit long rendering to get the final outputs. So can we take the same idea and apply it to GAN for image generation? So this is the goal we want to achieve in the any-cost GAN project. So the basic idea is that we hope we train a GAN model that can be run at diverse cost. So we can either run it at low cost to provide a fast interactive preview during the editing, and after the editing is done, we can run the full model to generate high quality outputs. So because this is done after you finalize editing or during the idle time, it's slow, but it provides the high quality final output. So the main concern is that we hope the output of the fast model and the slow model is consistent visually so that we can use it for output preview. If they are not consistent, then there's it doesn't really make sense to use the fast model for preview. Is there a question? Oh, okay, sorry. So to train a model that can produce consistent output at different costs, we are studying two dimensions. One is the resolutions, one is the channel numbers, because these are the basically two dimensions that affects the cost of the models most significantly. So let's revisit the style GAN 2, which is the state-of-the-art GAN model at the time of the project. So this kind of model, it also consists of generator and discriminator. So the architecture of the generator is basically upsampling along the inference process. So this is the resolution. So as the model goes deeper, the resolution goes higher. And because we are only training the model to generate high resolution outputs, so only the final outputs is fed to the discriminator. So essentially, the model can only generalize the high resolution output, something like 256 by 256. And there's also another work called MSG GAN that simply just feed all the intermediate outputs to the discriminator. So the discriminator will get inputs from all the resolutions. So in that case, the model can actually generate multiple resolutions because all the outputs are supervised by the discriminator. But the problem is that such design is breaking the balance between the training of discriminator and generator. Because for discriminator, now we have more information from the generator. Originally, it only has the highest resolution input, but now it has also the intermediate state from the generator. So it's actually easier for the model to tell the difference between real and fake. While for the generator, now you not only need to generate high resolution outputs, you also need to generate lower resolution outputs. So it's actually making the task more difficult. So this kind of change in difficulty will break the balance for generator and discriminator training. So to fix the problem, here we propose a simple modification called sampling-based multi-resolution. So instead of feeding all the resolution to the discriminator, we are, during each training iteration, we sample one specific resolution and just feed a specific sample resolution to the discriminator. So despite this simple modification, we actually get much better performance by using sampling-based multi-resolution. So here is some results. So for the single resolution result, it basically means that we are training a specific GAN model at this resolution, like just one resolution only, from 32 to 126, 1024. And for MSG GANs, it supports 4 resolutions for one single models. But as you can see, the FID. So here the score is one metric called FID, which is lower the better in terms of image quality. So for MSG GANs, despite one model can generate 4 resolutions, the FID is actually worse for most of the resolutions compared to the single resolution baseline. While with our modification, we can train one model to generate 4 resolutions, while for the 4 resolutions, the FID is consistently better compared to the single resolution baseline. So with this kind of simple modification, we are actually able to output multiple resolutions without like training multiple models, while at the same time improve the quality.
Did input which resolution?
Like by input, do you mean the noise or?
At the inference time, I want.
Oh yeah. At the inference time, at one inference, it can actually generate 4 resolutions. But if you just want the low resolution, you can do early termination here. So it no longer further upsamples. So you can just ask it to generate a low resolution by truncating the model in half.
So basically, with yours, your training less because you're not for every image, you're not generating for each resolution.
Yeah. So the training time should be faster because because we are sampling different resolutions, so some of the layers is grayed out. Basically, we are not running them during training, so it actually reduces the training cost a bit.
Given the same amount of training.
Oh no, we are actually training this on the same amount of data, so we are like training the same iteration. So it's not because we train longer, basically. I think the reason for better FID is that it has also been observed in other papers, because when the model is too deep, you try to feed a supervision for an entire generator. Sometimes it's inefficient, but if you feed intermediate feedbacks, it actually regularizes the model to learn better for the generator. Yeah, thanks. And here is like simple visualization. Original style GAN tools in the intermediate outputs doesn't really make sense, but with our model, we are able to generate different resolutions. And the second part is how we can train the model to support different channel numbers. So this is very similar to neural architecture search. We simply sample different channel configurations during training, similar to resolution. And there are two problems we need to face. The first thing is that the GAN training only guarantees the output is realistic. By realistic, it means that it looks like a human, but it doesn't actually encourage the consistency between the different channel numbers. So like this is the full channel, this is half of the channels. The outputs are not really alike, but this is easy to solve. We simply add a distillation loss between the different channels outputs. So it encourages consistency. And the second thing is actually more weird. So we also train like we compare to the vanilla baseline that basically we just train a single model at a certain channel configuration, and we also train our model that can run at different channel configurations. So one interesting thing is to notice is that for some channel configuration, the FID of our unified model is better in green, and for other channel configuration, it's actually worse. So we hypothesize that this is because if you use one single fixed discriminator, it doesn't provide effective feedback for different subgenerators, because the artifact for the full generator and the reduced channel generator may be different. So if you use single discriminator, it cannot effectively distinguish between the different capacities. So the modification is also quite simple. We simply just make the discriminator aware of the generator's architecture. So the way to do that is we simply encode the architecture of the sample generator in a vector, and we use a simple linear layer and use it to modulate the output of the discriminator, just to make the discriminator aware of the generator's sampled channel configuration. So this kind of simple modification also makes the FIDs consistently better compared to the single, like the vanilla model trained at the reduced channel capacities. So effectively, we are already providing a very good method for model compression because it's better compared to a smaller model trained from scratch. So here are some like visualizations. So this is the human data set, human face data set. This is the car data sets. So we're running it at different resolutions horizontally and different channel numbers vertically. So this is the interpretation between the different latent vectors. So as you can see, like for different inputs, outputs are very different. Actually quite similar, like virtually, despite the model here and the model here, they may have about 100 times gap in terms of computation. And similarly for the car data sets, like we are also generating like semantically consistent outputs. Like because we are training the model with a NAS-alike method, we can search different models with different like computational budgets, so that it can still can be used at different budgets. So here is a quick demo. We use the model to for face editing. So this is a Ryan image, and we are firstly we are projecting into latent space. This is the reconstructed image from the GAN outputs. Because we do the projection, we can now edit the image. So to begin with, we are using the full model to do the editing. We add smile to the face. As you can see, it takes about more than 3 seconds to finish the output, which is quite slow. This is why we want to like accelerate the editing. So there are two slide bars. One allows us to adjust the channel configurations. One allows us to adjust the resolution. Let's say if you for resolution, we can already make it to 1.33 seconds at a reduced resolution, but now we also reduce the channel numbers to make it in about 0.5 seconds. Yes, please. How is the channel dimension? You mean the image output? Yeah, so we only change the channel for the intermediate feature maps because yes, like after we add it, we can click the finalize model to render the high quality outputs. Yeah, let me get back to you. So basically, the final output is always 3 channels because it's an RGB image. So by reducing channel numbers, it means that we only reduce the channel numbers of the intermediate layers. So this is another example. Basically, we are using the like accelerated model to run the outputs. And as you can see, if we want to make it older by gray hair, there will be artifacts like a glass is appearing in the face because during the training set, wearing glasses and older is correlated, but we can make some adjustment again to reduce the eyeglasses effect. And we can, after finalize, we can click it to generate high resolution outputs. Like it's more clear with more details. Yeah, so this is the rough idea how we can use a dynamic cost GAN model for image editing to make it more interactive. Okay, so the third project is not about model efficiency, it's about data efficiency for GAN model training. So we all know that data is expensive. So if you want to train a GAN model, it probably requires of million scale data to train a good model. So if you want to curate such data, it's super expensive. For FFHQ data sets, it's 70,000 images. So it's unlabeled, but it's crawled. Still quite hard to curate a high quality one. But on the other hand, ImageNet is even more expensive because you need human to label the categories. So unfortunately, GAN models are very sensitive to limited data. So if you have fewer data for the GAN model, the generated output is going to be pretty bad. So this is some sample images we collect for generation, like 100 images for Obama generation. There's a lot of artifacts. It doesn't really form a person. And also for cats and dogs, it doesn't really, it gives you a very artistic effect, but it's not real. So this is definitely something we want to improve. So here is some like more quantitative data. As we mentioned, FID is lower the better. If you use 100% training data, you're getting good FIDs. But if you're reducing the number of training data, the FID is much worse. So we find the problem of the data size and like bad outputs is actually of course about overfitting. So here we are plotting the discriminator's accuracy during training and validation. So a recap that the discriminator is trying to tell the image you feed in is real or fake. So this is 100% data we use for training. We already observe a little bit overfitting for the validation set. But if you only use like 20% of data for training, then the overfitting on the validation side is much worse. And if you further reduce it to 10%, then the overfitting is even worse. So because the discriminator is overfitting, so it doesn't really provide an effective signal to train the generator. So in that case, we cannot get a good generator model for some image synthesis. To combat the data overfitting problem, data augmentation is one of the very popular ways when we try to train an image classification model. So for example, this is a cat image. By data augmentation, you can, for example, rotate the data or zoom in, zoom out of the data, or sometimes you do some like shifting along the spatial dimension. But this is all very natural. If you want to train an image classification model, you simply augment data and use the original label to train the model. But the problem is, how do we augment the GAN models with data augmentation? So recap that during the GAN training, the generator and discriminator is trained iteratively. So for one iteration, we are training the discriminator with the frozen generator providing input and real image as input to tell real or fake or false. And during the training of generator, we are freezing the discriminator to provide some feedback. So the first option is we simply just augment the real image during the discriminator training. So this is like simply similar as image classification problem where you simply like augment the real image. But the problem is that because you are augmenting the image, let's say you are augmenting with color jittering. For example, you are making it a little bit gray or making it a little bit dark. So the output image, you also have such kind of artifacts from the augmentation because the discriminator only see the augmented image. So you require the generator to also generate augmented image. So this is from color jittering. And if you also add spatial translation, then the generate image, you also have spatial translation. So this is definitely not something we want. And there's also another augmentation called cutout, which is even more weird. So basically during training, you simply cut out a patch to reduce overfitting. But the generate image, you also have cutout. So this is definitely not desirable. A way to address this problem is actually quite simple. We simply also add the same augmentation to the generator so that the generated image could be without artifact. Then after the augmentation, you have the similar like augmented effect compared to the real image. So we don't require the generator to also generate those augmentation effects. But the problem is that it's due to the unbalanced optimization. So because for discriminator, we are making the task even more difficult because you need to distinguish between the augmented images, which is more difficult compared to distinguishing between the real and unaugmented version. Because if you add color jittering, it's more difficult to tell the real or fake data. For example, if you make it more like darker. And on the other hand, like during the generator training, there's no such augmentation. So this is kind of imbalance for the training. So so the model only get high accuracy for the augmented outputs for the discriminator, but for the unaugmented version, it doesn't really give a good supervision because it doesn't get a high accuracy on an unaugmented version. So the answer is actually also very simple. We simply also add an augmentation here. So the basic idea is that we want the augmentation to be differentiable so that we can propagate gradients, but we want to add it both to gradient generator and discriminator and add it to both state of the training. So in this case, let's say for example, we have two images. We run it through like the same like random data augmentation pipeline, but we want to make sure it's differentiable so that we can still have the gradients flow back to the generator to improve the to reduce the overfitting problem. And again, we need to differentiable so we can flow back the gradients. So here we look again at the FID. So after the data augmentation, we are improving of FID consistently for different data amount, but the improvement is definitely more significant for fewer data scenarios. And here are again the comparison of the very low shot generation experiments. So this is 100 shot Obama. So it now looks at least somewhat similar to Obama, but not some like weird outputs. And similarly for dog and cats, we observe a much better quality for the low shot setting. And we are also doing some interpretation experiments to show that the model is not just feeding to a few of the training samples. It can get some like so basically for this kind of scenarios, for this kind of samples, we simply collect a bunch of the images from Google about this thing. So it's actually not really possible to get hundreds or thousands of images for a certain thing. So this again, like emphasize the importance of a few low data generation. So this is done all by providing only 100 images. Okay, so this concludes the part for the GAN model. So maybe we can take a little break and we'll come back in 5 minutes in 4:12. Yeah, thanks. Okay, welcome back. So so next we will talk about So next we'll talk about efficient video understanding. And so this is about recognition model. So it's not about generative model. Okay, so videos are growing exponentially. So at the time of the project, I think it's 2019, there are about 10 to the 5th order of magnitude hours of video uploaded to YouTube every day. So it's still growing like exponentially. So for YouTube, you do need to process the video for example, like classification or recommendation, and also like you need to do it for like censorship or whatever, just to detect the harmful contents. So they do need to process all the videos on the cloud, and this kind of processing is usually very expensive. So even for YouTube, is a lot of cost. And on the other hand, we also need to do video recognition on the edge. For example, like in healthcare cases, sometimes people deploy those cameras to detect whether an elderly person is falling to the ground or something like that. So this kind of application actually runs the model on the edge device. So you also get the constraints from the energy or the latency. Here are some like more concrete examples of the application of video recognition models. So this is the like hand gesture recognition. You are doing hand. I think a lot of the cars nowadays have this kind of features. For example, like BMW, you can just do some weird gesture to control the music play or something. And this is the example of movie understanding. So basically, try to understand each person what they are doing. And here is like the video prediction for autonomous driving. So for example, here is a person. We want to predict that the person is going to walk straight. So you don't want to hit the person. If you can predict it a few seconds earlier, you can make the decision earlier. So the main difference between video processing and image processing is actually about the temporal information. So here is an example, like 4 frames from a video. So if you look in this arrow of time, you see the person is moving this thing from left to right, and if you look in the other direction, it's vice versa. So video processing is all about temporal modeling, apart from the image, like spatial modeling part. So there are different ways to do video modeling. The first thing is, the most simple way is to do 2D CNNs. You simply apply 2D CNNs to each frame of the video. So this is a action recognition model. So we are trying to figure out what the person is doing. So let's say if you do a 2D classification of each of the frame and aggregate the scores, you can get a person is doing parallel bars. So this is actually quite strong baseline if you are doing some data sets like this, which doesn't really consider temporal informations. But if you are doing like temporal related data sets, then that's definitely not going to work too well. And the second thing, like if you still want to use 2D CNNs, and if you want to consider temporal information, one thing is we can do is called two-stream CNNs. So apart from the RGB inputs, we also calculate the optical flow. So for optical flow, it basically means that for given 2 frames, we're trying to compute the movement of each pixel in the frames. For example, like this is the dense optical flow for each of the location, and you can feed in those optical flows into another 2D CNN streams and aggregate the scores. So this is for spatial reasoning, this is for temporal reasoning. So it allows you to still use 2D CNNs, but you can take into consideration of the temporal information. But the problem is that the optical flow is super slow to compute. It's usually more orders of magnitude slower than the ConvNet backbone. So it's not really going to work for the sake of efficiency. A more natural way, also another thing is that we simply run 2D CNNs to extract the features and plug in an LSTM to the end of the model so that it can also model temporal information. But the problem is that we only do, when we do this kind of post-fusion, we are losing the low level details. For example, we are not able to model some like correspondence between the fine grained details. For example, if a ball is moving, it is probably too small in the feature map, then you're not going to model the difference. And another way to address all these problems is to simply use 3D ConvNets. So by 3D ConvNets, it means that it not only convolves along the height and width dimension, it also convolves along the temporal dimensions. So in this case, the model has a 3D convolution kernels, so it can jointly model spatial and temporal information. But the problem is that the computation is, of course, larger. And also, because of more parameters, it's very easy to overfit. And video data sets usually have smaller size and diversity compared to image data sets. So this is making things worse. So another way called i3D basically address this problem by initialize the 3D CNNs with a 2D pre-trained model, for example, trained on ImageNet, and then inflate convolution kernels along the temporal dimension. For example, this is a 7x7x7 kernel. You first start with a 7x7 2D ConvNet kernel, and you just repeat it 7 times along the temporal dimension as an initialization. Yeah, so this helps us address the overfitting issue. But the problem is that the computation is still large. For example, 7x7x7 is 7 times larger than simply 7x7. So this is making some like constraints for edge deployment. So the cost is large model size and large computation. But a pro is that it can model both low level, middle level, and high level information interactions because you are adding in the temporal modeling from the very beginning of the conv layer. So the question is, can we achieve 3D CNN's performance at 2D CNN's cost? So this is our previous work, temporal shift module, or for short TSM. So the basic idea is super simple. So instead of using 3D convolution, what about we simply shift part of the features along the temporal dimension to exchange the information. So here is a feature map. It has 3 dimensions. This is the temporal dimension. This is the channel dimension. And here the short axis here is the spatial dimension, height and width. So what we do here, so as you can see, if you use 2D CNN applied to each of the frame, so each row only has 1 color, which means that it has the information only from the current frame. But if you apply some kind of temporal shifts, basically shifting between the temporal dimension. So for some of the channels, let's say for the first channel, we're shifting by 1 along the temporal dimension, and the second channel was shifted by 1 in the other directions. So after this kind of shifting, we are having 3 colors in the line, which means that we have information not only from the current frames, but also from the neighboring frames. So of course, this is offline video processing where we already have the future frame, so we can shift bidirectionally, similar to a BERT model where you have attention bidirectionally. And in some cases, when we try to do online video recognition, basically we are performing modeling on a streaming video. We only have the history frames, but we don't have future frames. So it simply shift from past to future, but not the other direction. So the advantage of the TSM module is that it's simply an address shift. So there's no cost in terms of parameter count or the number of computes, because simply we just shift the part of the memory, and it can be fused with the later convolutions to actually help you get rid of the memory like manipulation cost. So when you try to put it in a convolution neural net, we simply insert it in a 2D conv nets. So between 2 convolution layers, we're simply adding a TSM module. And here we use an identity mapping or residual connection to bring back the information that is lost, like the white here, from the shifting operation, so that you can still have all the information from the current frames. But by shifting, we're able to incorporate the information from the neighboring frames as well. And for the online settings, because we are processing the video frame by frame, so this actually works like an RNN. So basically for each frame, we simply ship out part of the channels and store it in memory. And for the next frame, we simply replace the features with the history features, and then again ship out the current features into the buffer. So it basically performs like an RNN. So it can work in a streaming fashion. So the implementation is super simple, just a few lines of code. And compared to the baseline, like for example, i3D, as we mentioned, and also another efficient video baseline. So we are comparing accuracy versus the computation. We are like, we're having a much better like trade-off curve compared to the other 2 models. And here is a demo about running a TSM model on something data set. So basically, it's an object agnostic data set, just model the relationship. So the model can get some like quite high quality outputs. For example, it says cover something with or whatever. So basically, the model can correctly handle the temporal relationship between these frames. So these tasks are all require temporal information to get the correct labeling. So if you look at a single frame, it doesn't know what is happening here. Here are some visualization, compare the latency and throughput compared to the i3D model. We are getting higher accuracy, but with 9 times slower latency under batch size of 1. And with batch processing, we are getting about more than 10 times higher throughput while getting higher accuracy compared to 3D conv nets. Yeah, so here is another more interesting version. It's about how we can use the temporal information to help us improve the object detection. So when you do the self-driving cars, you're basically performing object detection for each of the incoming frames. But there could be some cases, for example, like when a car has a headlight against you, so you get some glares in the camera. So let's say for the example on the right, like you're detecting the car, like on the left-hand side is the 2D per frame detection. On the right-hand side is the considering of the temporal information. So when you have the glares, you have some like mis detections, but with the help of temporal information, the model can get to know that the car is still a car because you can consider the previous temporal information to help you get rid of the silly mistakes. So here is just some comparisons. So this RFSCN is a classic 2D baseline, and online TSM means that we are inserting the online version of TSM into it. So the latency is exactly the same. But for the MAP on different objects, when the object is moving very fast, we are able to significantly improve the detection quality because we consider temporal information. Now, on the other hand, we have some like numbers for deploying these TSM models on very edge devices like Raspberry Pi. So we are getting like some really good FPS in real time on smartphones doing video recognition. And on the other hand, we also try scaling up the training of these models. So at that time, we work with Summit supercomputer. At that time, that is #1 in the world. So we try to do some like distributed training, and we find the scalability of the model is actually quite good. So we can accelerate the training of the model about 200 times by running on 128 Summit nodes, which corresponds to I think 500,000 of GPUs, so that we can finish the training of the super large video data sets in about 15 minutes, from like single node training 2 days to about 15 minutes, showing the scalability of our model. And this is like basically the scalability result compared to i3D models. So we are getting better scalability. So this is all log scale. But because we have fewer parameters compared to the 3D models, we are making the communication between the nodes easier. So we are observing a better scalability compared to those 3D models. And finally, we have some like dissection results. So by dissection, it means that when a video makes a prediction, when we train the model, we want to figure out what the model is learning about from the data sets. So we dissect each of the channels from the very output. We find different channels actually encode different semantics. For example, one specific channel, when we try to figure out its attention map, basically these dark light regions are the spatial regions the model is looking at. For example, in this channel, the model is looking at moving something away. So it only lights up when actually the person is moving the cup away. But for the static scenes, they are not lighting it up. So similarly, like this channel, another channel actually learns to recognize the activity that push something to the left. For example, this only lights up when people is actually trying to push the mug or the glass. And here is another fun demo that people is building with our model. So like this is hand gesture recognition running our TSM model on edge device, and they use it to manipulate or navigate through the Google Map. Yeah, so this is our gesture recognition. Okay, so we are running a bit fast because we still have a last section about the point cloud recognition to go through. So let me know if you have any questions about the video part. Okay, cool. So let's go to section 3 about efficient point count recognition. So previously we talked about image and also videos. They are all kind of regular data. But for point cloud, it's not regular, but it's still very important. For example, self-driving cars nowadays, like apart from Tesla, like the one from Waymo, or like Cruise, they all use a LiDAR sensor, which generates point clouds. And for VR headset, because you need to position the headset, the location of the headset in this spatial area, so you try to track your headset. So you also need like LiDAR sensors to get the depth. And also we have LiDAR scanner in iPhone and iPads in the latest version, and people also use it in drones to help you navigate, so that you can prevent the drones to like just run into some like walls or something like that, just break the drone itself. So this is a typical visualization of the LiDAR sensor, and this is collected from a self-driving scene. So by the representation of the LiDAR is different from image. For image, it's pretty regular. So we have an image of certain height and width. So you have an array or a matrix or a tensor, like in 3D, to store those values. They are all continuous in memory. But for point cloud, because these point clouds, they don't have a like fixed order, so they're actually using quite randomized format to store this point cloud. So for each of the frame, we're encoding the point cloud using a collection of 3D points. So the P here is the 3D location of the point in the area, and the F here is some features. For example, typical features include the strength of the point cloud, because if you cast a ray to the certain object, some of the information, the ray may be partially reflected away from the surface, so you get different strength for different point clouds. So basically, F here encodes all kind of features about this point cloud. And because all these 3D points, they are not continuous in somehow, it's hard to find a fixed order for all these points. So all of them just store like discretely. So they don't have any like spatial like continuity. So you simply just store each of the points as a set instead of an array or something like that. So here is another example of the LiDAR signals. But you can basically people perform object detection in the LiDAR signal space and try to visualize it here. So this is just because the LiDAR is like rotating, so you have these different like circular patterns here. And this is another application about indoor use case where you use a LiDAR sensor to scan your room, and the model can do some semantic segmentation so that after you just carry the sensor around the room, and you can generate a 3D layout of the entire apartment or the entire building. So as we mentioned before, images are dense and regular because for a specific pixel, like a pixel here, you already know that the neighboring pixels are just the 8 pixels around the specific pixel. So you know where to look for it in the memory because they're just stored nearby. So it can easily be processed by conventional conv nets. But for the point clouds, they are extremely sparse. So as you can see, only the color points have some collected point clouds. And for most of the area, for example, between me and the wall, there's nothing in between. So there will be no points if you use a LiDAR sensor. So they are quite sparse, usually smaller than 1% in terms of density. And they are quite irregular in the memory. Let's say, for example, if we want to find a specific point here, if you try to find its neighbors, they don't have a specific neighbor, so you need to run some you need to calculate this distance between this point and all the other points to find its neighbor. So if you are trying to apply convolution, the main idea of convolution is to process the current entry with its neighboring entries. So for each convolution layer, you need to find all its neighboring points. So it's going to be quite costly if you just simply apply convolution to the model. So this kind of computation problem is actually quite worse because for LiDAR applications, for most of the times, we do need to run it on edge device. Either it's a VR headset or even it's a self-driving car. So for early self-driving cars, we need the entire trunk to store those workstations. And if you are running an EV, then probably it's going to drain your battery, making you drive shorter range. So that is definitely not possible. So we also need an efficiency improvement for LiDAR processing. So as we mentioned before, the LiDAR is very irregular, so it's hard to process. So one way people come up is to make it more regular. It's called voxelization. So basically, you can imagine if you are scanning LiDAR points in this classroom. So the classroom by nature is a more regular shape. So how about we just voxelize the entire classroom with a certain resolution? For example, every 10 centimeters is a grid. So we simply just put those get LiDAR points into the grid. But the problem is that we need a high resolution to get all the LiDAR data point cloud data points into the specific grid. So, but if you use a high resolution, the memory of these voxels can be super large because it's 3D. So imagine if you have 10 centimeter resolution, then probably you have like hundreds of millions of voxels just for this classroom. So as you can see, as the resolution goes higher, the GPU memory usage also goes super high. And on the other hand, so if we want to distinguish every two point clouds data samples, we don't want to map a lot of the data samples into the same grid or same voxel. So we need a higher resolution. So here we also measure how many data points are mapped to the same voxel if you use a certain resolution. As you can see, if you run things on 8GB GPU memory, here we are losing about 40% of the information because 40% of the points are mapped to the same voxel. So voxel is easy to process because it's regular, but it's not really memory efficient. And most of the voxels are actually empty because the point clouds are super sparse. So on the other hand, how about during each of the convolution computation, we simply just gather the neighboring frames by pre-computing some nearest neighbor informations and then just do the convolution. But the problem is that if you try to gather the neighboring points, these are all irregular memory access instead of computation.
So if you profile the previous method, like DGCN or PointCN or SpiderCN, actually the effective computation is super low. So over all the inference time, like for these two models, less than 20% of the time is spent on the effective computation, but most of the time is spent on gathering the neighboring points to help you to prepare for the computation. So usually the more compute you have, the higher accuracy you have. So this means that those model also doesn't have a high inference efficiency because only less than 20% of the time is done for the computation. And on the other hand, like memory operation is actually more expensive compared to computation. So here we compare the energy usage of multiply and add, which is computation, and also memory for SRAM read and also DRAM read. So if you compare the energy usage, because the voxel is because the point cloud is large, you cannot fit in everything in SRAM. So you put most of them in DRAM. So then the memory compute usage is about 20 times larger compared to the computation. So even if you don't care about the latency, the energy usage will be very large if you are doing some fancy memory like manipulations. So one way our lab has been working on is called point voxel CN to address the problem. So the idea is super simple. It's a two-branch architecture. So for the one is voxel branch, and the other is a point branch. So for the point branch, as we mentioned, if you try to gather the neighboring points, it's super slow. So for the point branch, we simply use the MLP. So we are not modeling between the relationship between the points. We simply just do feature learning. So in that case, we don't need to gather the neighboring points. So it's more efficient. And because we have this point branch to handle the high resolution details, we can actually use a low resolution voxel branch to just like do the model the spatial like relationships. And because we can use a low resolution, it doesn't use a lot of GPU memory. So this kind of two-branch design can help you get benefits from both regularity from the voxel branch, and also it can also help you get rid of the irregular memory access in the point branch while still give you a high resolution information. So here we visualize the feature maps from the voxel branch and the point branch. So these are some like smaller scale data sets of 3D 3D point clouds. So some furnitures. So as you can see, because the voxel branch is low resolution in nature, so when you try to visualize the heat map, this branch focuses most on the general large structures, while for the point branch is focusing mostly on high resolution details like those details. So if you put them together, it will give you a better balance by focusing both on the rough structure and also the fine-grained details. So now we compare the semantic segmentation accurate IOU, which is a metric that is higher the better, and also the latency. So these dotted lines are our model called PVCNNs. So these are basically the two-branch design. And compared to the baseline, like for example, this is SpiderCN, we are able to get comparable accuracy at 8 times faster inference speed. And on the right-hand side is the accuracy versus the GPU memory. We are also getting much better trade-off in terms of accuracy and memory. Here are some like demos for indoor 3D segmentation. So given the input scene, we are trying to segment them into like different regions. For example, this is chairs, this is floor, this is wall, or something like that. So compared to point nets, we are like using like about twice faster while getting even better accuracy, I think. And this concludes our previous two-stream branch. So as we mentioned, we propose something called PVConf, which is just a two-branch design. So we're using a low-resolution voxel to model the spatial relationship, and using a high-resolution, simply like MLP, to process the high resolution informations. But we don't model the interaction between points. But the problem is that later they still find even using a low resolution voxelization can lead to information loss. Like for example, this is the input scene. like you can see a car and a person, and this is the low resolution voxelized representation from the PVC and like the previous work. So because of the low resolution, you cannot really see that this is a person or this is a like some like traffic stop, and you cannot see this is a car because the resolution is so low. So in this work, we are replacing the original low resolution voxel with the high resolution voxel. But as we mentioned, this comes at the cost of high GPU memory. So we don't want to do traditional convolution. So instead, we're doing a sparse convolution. So by sparse convolution, we mean that the convolution no longer applies to all the regions in the voxel. Instead, we only apply the convolution where there is a point. For example, this is just for illustration. So we are dividing the voxel into multiple grids, and we only have the points here. So we no longer convolve all the entire voxel. We only convolve the voxel that contains the points. So in this case, we are able to, with this new primitive, the sparse convolution, we are able to use a high resolution voxel, while at the same time we do not blow up the GPU memory, or we do not have a super long compute latency. So it gives us a better accuracy and also better efficiency. So with this kind of modified design, we look again at the point-based branch, like basically the lower branch, which is point-based, and we can see that it mostly still focus on fine-grained details. For example, like those like traffic signs, these are super small in the like point cloud compared to the entire scene. So the point branch has higher resolution, so it focuses on these regions. And finally, like we also do neural architecture search. Basically, this is a general technique to help you improve the accuracy efficiency trade-off. So we always do, like we can always do neural architecture search to improve the efficiency. So similarly, we are doing just like channel or whatever search to improve the efficiency of the model. And for other work, there's also, like as we mentioned, we have two representations. One is voxel, the other is point. And later, people also find it's actually possible to add even more representations for the same scene. For example, a later work, they propose something called range image. So this is basically about projecting the point cloud through your lines of view, so that you get a 2D mapping of the range of each pixel. So imagine if you are driving, you look at the frontal view, and you can get the depth of each pixels. So they also feed in the range image to the model, which also gives you better accuracy. So this is about how we utilize different representation of the same scene to help you give you more information while it doesn't break the efficiency. Because this range image is simply a 2D image, so it's super like lightweight to process. So these are like all the tasks we used for, like we did to improve the efficiency for point cloud modeling. But in real life, in a real driving car, like this is one from Waymo, you not only have one LiDAR sensors, actually you have three kind of sensor. One is camera. Actually, they have 10 cameras on a single vehicle, and 5 LiDAR sensors, and also 6 radar sensors. So in actual cases, you are not only doing recognition based on simply on point cloud inputs. You are trying to do recognition based on all these sensors. So we actually need to fuse the information from all these sensors together. So this is a problem we are trying to address in the BEV fusion work. So why it's called BEV fusion? So the problem is that, like, this is the multi-view RGB image from the camera. So it's look at each camera look at a specific angle from the vehicle, and this is the sparse feature from the point cloud. So the problem is that the point cloud is 3D and the image is 2D. So how to align those sensor information together so that we can effectively fuse them for prediction. So so essentially, we're trying to find a space that can align these two modalities. So actually, one very interesting good space is the BEV space. So BEV is short for bird eye view. So basically, it's this kind of space. You are looking at the driving scenes from top to down. So we are looking above the vehicle from the sky. So this is why we call it bird eye view. So we find fusing the representations from the bird eye view space is actually quite effective. So for LiDAR, because it's 3D, you can actually rotate the LiDAR into any kind of angles. So here for LiDAR, we simply just rotate it to look at the bird eye view and then just flatten it, which means that we flatten the LiDAR representation from the z-axis, which is the vertical axis. So we are trying to flatten the LiDAR space along the vertical z-axis into a 2D map in BEV. While for the image, it's actually more complicated because for image, we are looking at, for example, we're looking at the front, we're looking at the side. So how we can project into BEV? So the idea is that because we know the orientation of the camera, and we can also ask the model to predict the depth of the image. So for example, model can predict the car is closer and the sky is farther. So with the correct orientation and also the depth map, we can actually calculate the projection transform so that we can transform the image features into the BEV space. And finally, we simply just concat the features from the camera and also the LiDAR after projected to the BEV space, and then just use the fuse feature to do some tasks. For example, we are doing map segmentation, like segmenting the driving lanes, and also do 3D detection based on the BEV scene. So we find projecting array features into the BEV space for the fusion is very critical for the accuracy. So this is why we try to emphasize the BEV fusion name in the project. And here is a demo about the BEV fusion. So this is just 6 LiDAR camera inputs, and this is the LiDAR inputs. So as you can see, this is the frontal view, this is the back view, and we're trying to segment the map of the driving area. So these are all map free. So basically, we are doing on-the-fly segmentation based on the sensor inputs. So as you can see, the final outputs look pretty convincing. You can get a boundary, get a turn, and also the lanes for different inputs. So one good thing about the sensor fusion is that if you use camera only, then at the night, because it's super dark, you cannot get effective information from the camera only. But with BEV fusion at night, you also get LiDAR, and the LiDAR signal is not disturbed by the illumination or lighting conditions. So you can, by fusing multiple sensors, it can give you more robust representations. So despite Tesla mentioned vision alone may be able to solve the problem, but definitely adding in more sensors can give you more redundancy, especially in bad conditions like at the night or raining or snowy conditions. And here is some benchmark results that people try to compare. So at the time of the submission, I think it's 2022, there's a Olympic for self-driving perception problems. This is the Waymo leaderboard. At that time, I think our BEV fusion work gets the #1 if you look at a specific metric. I think this is the most widely metric people try to use to rank the methods. Okay, so I think that concludes the talk today. So today we are mostly looking into domain-specific optimizations for image generation with GANs, and also video recognition, and also point clouds with 3D recognition. Yeah, thank you so much for attending. I think we can end a little bit earlier.